Good afternoon and welcome to our last brown bag seminar of this season, sponsored by the St. Croix River Association. Our speaker this afternoon is Scott Alexander from the Department of Earth Sciences at the University of Minnesota. Scott has 20 years of experience in working on projects related to groundwater flow and karst systems, contaminant migration in many variety of geologic settings, including microbiology and brines, multi-phase, multi-component fluids, and carbonate rocks, and various rock systems. His current work focuses on rainwater reuse and geothermal heat pump systems. Today, Scott will be talking about the ISOP process in Minnesota. So please welcome Scott Alexander.
Thank you. So this is kind of a little side project. If you're doing research, one of the things I've found over the years is you need kind of a hobby and always be watching for interesting new phenomenon that maybe you can turn into something interesting. In terms of lake ice off, if you've ever lived or spent a lot of time around lakes, one of the most anticipated times of the year is the ice off. You spend all winter tucked away in your little cabin, and when the ice finally goes off the lake, that means summer can begin. You can get out on the water and start the whole summer. It takes a lot of patience to wait for the ice off, though, because it's one of these things, it seems like the lake ice hangs around forever. In the picture here in the title slide, you can see the snow is long gone, but the lake ice is still there. So up on land, it seems like winter's over. Things are starting to green up and perk up for the spring here, and that lake ice, that darn lake ice, is just hanging on. It's here. So lake ice is one of these fascinating things. One of the observations that people have made, and you hear from the old timers all the time, is that when the ice finally does go, it disappears really quick. And some would even tell you that it sinks to the bottom of the lake. And as a scientist, I know the density of ice is always less than water. Ice, no matter how many holes you put in it, isn't going to sink. But the observation of these old timers was absolutely correct in that the ice, once it decides to go, it disappears in literally hours. So something seems to be going on here where that ice can persist for a very long time, but then once you hit some threshold, that ice disappears very, very quickly. And so the Minnesota Department of Natural Resources here has a nice description of the process, and basically stating that, yep, the ice doesn't sink. It just seems to melt very quickly. We'll put a little caveat out here. If you're going to study lake ice, particularly as it thins, you will sooner or later go through. And playing around on thin ice like this, I think the local sheriff might be a little unimpressed. What exactly were you doing out there in the middle of the lake playing on thin ice? Good luck. Obviously, the water is going to be very cold. So that's definitely a danger. The other danger that you might not think of is the melting ice as it becomes very honeycombed and forms these candles, long, slender crystals of ice. It becomes very, very sharp. And so going through rapidly thinning ice, you're going to get cold, but you can also get really cut up. It'll slice right into you without any effort. So that's a warning. Don't play on thin ice.
From experience.
We're going to start out here with a little lake just 10 miles or so north of Stillwater, Square Lake. This is a lake that I've spent a lot of time on. My family's had a cabin on this lake for 65 years now. So we've got a long history on the lake here. And basically it's a great playground for a kid. In recent years, it's become a very high interest lake. It's a very clear lake. It's always been very clear. It's rather deep. And there's relatively limited development around the lake. The steep shorelines going down to shore. Most of the cabins, you can see it here, are set well back from the shoreline. So unlike a lot of lakes, it's not built up right to the shoreline. And then we have several large properties on the county park here on the east end. On the north side is a privately owned parcel that's in some kind of conservation reserve. And then on the northwestern side is the Wilder Forest, owned by the Wilder Foundation. So it's a rather well protected lake, deep, clear water, and those deep, clear waters are also quite cold throughout the summer. And so the DNR has spent a lot of time setting this up to do a dual layer fishery. They have the warm water fishery, bass, northern panfish in the shallower waters, and in the deep waters they have been trying to stop trout. So a few years ago, 2 years ago, back in 2013, I had some new instrumentation. It was some equipment that could do profiling in monitoring wells. Could measure temperature, conductivity, dissolved oxygen, and it had a 30-meter long cable. And so I thought, well, let's go play around with this, see what we can do. And went out on the lake a few times through the winter. Got out there in mid-March here. It's the red line. And got a nice temperature profile. The water temperature in the ice, or through the thickness of the ice, was close to 0 Celsius. Not too unexpected. And then as you got below the ice, it very quickly warmed up to about something close to 4 degrees Celsius, which is where the maximum density of water occurs. So that colder water up on top is actually floating. It's slightly less dense than the water beneath it here. So that made sense. And then way at the bottom, you get down here 55, 60 feet. The maximum depth from the lake is 65 feet. You get a little bit of a geothermal gradient where that water warms up just slightly over the maximum density of water. So that looked perfectly normal, acceptable. As we got closer, as we went into April, we basically warmed up the water column, and more of that water column warmed up to the 4 degrees Celsius mark. So in the dead of winter, you're basically starting to cool down the whole lake from the top down. And this is a fairly slow process. The water's stratified. There's no physical mixing through there, so it's all diffusion of the temperature through the water column, which is going to go fairly slowly. So we started warming up, and then as we got quite close, get down here, mid-March, we had 28 inches of ice. On April 27th, we had 12 inches of ice, and something interesting appeared. Suddenly, the water underneath the ice was warmer than that 4 degrees Celsius, and it was actually quite warm. It got up 6 or 7 degrees Celsius, which is probably getting up to 45, 46 degrees Fahrenheit, so much higher than 32 degrees Fahrenheit, well above the maximum density of water. So this stuff should actually be, this Marmol out here, should be lighter than the water above it. And yet it seems to persist here. And the interesting thing is we've put in quite a significant layer here. The that 6 degrees Celsius mark extends almost down to 10 feet of depth. And then even there's some warming down to even 20, 25 degrees or 20, 25 feet below the water surface. So what we've done here is stored a tremendous amount of solar energy in the water column. And if we could somehow that water column gets disturbed, the heat to melt that ice already appears to be in the lake. So I thought that was very interesting. And then, of course, the next day the ice went out, so that kind of ended the process.
How were you out there? Being low?
On 12 inches, if you go out in the morning, it's actually pretty walkable. We were wearing PFDs just in case. And as the ice gets thinner, we'll also tend to pull a kayak behind us. So you can, if you got into trouble, you have something to crawl into and get out of the water.
Were you walking across water to get onto the ice?
Yeah, usually there'll be a small gap. Sometimes you can step over it, but it'll expand along, the ice will melt out along the shores first. Although as it happens, our cabin is on the south shore, so that shore actually melts out last. On the north shore, there's probably 20, 30 feet of open water. So as we go through the ice formation process in the fall, which is another big event on the lake, getting that ice to form and then stay, basically seems to end the open water season and put you into new mode. What we're looking at here is the augered hole when there was still about 2.5 feet of ice on the lake. And there's a couple distinct layers. As you go deeper in the hole, about halfway down here, the ice becomes much darker. And that's the nice clear ice that basically formed as the water froze and then was, it's the ice that's freezing onto the bottom of the ice pack. So it's crystallizing very slowly. There's very few air bubbles trapped in there. And so you get a thick section of very dark, clear ice. And then above it, you have a lot of air bubbles. And that's mainly from the snowpack that lands on the ice. And then that added weight basically pushes down on the nice, hard, clear ice below it. And water will flood up under the snowpack and refreeze. So you get a layer on top of that hard, clear ice underneath here. Underneath, it's kind of here, you'll get a layer on top that's a little less dense. It's got a lot more air bubbles. And then with the snowpack on top, it forms a very reflective surface. So any sunlight that would be shining down at the lake at this point, most of that solar energy is just being reflected back to the atmosphere and out into space. So as we add snow, we're slowly thickening the ice pack from the top side as you add that snow, and then as water seeps in due to the extra weight. And while that's happening, if it's still cold out, you can be adding ice to the bottom of the ice layer by freezing from the bottom side. As we melt it, what we're really melting initially is that top bubble-rich surface layer. So the ice underneath, that hard, clear ice, isn't losing much thickness yet, because very little solar energy is actually getting down into the water column. Most of that solar energy is reflected, but any dust or debris on that surface in the snow is going to absorb a little of that solar heat energy, and so that surface layer tends to melt out first. So we're seeing here at 2.3 feet that surface layer is thinned quite a bit here, but we still have a fairly reflective surface. Moving into April, the ice is thinning, and now that superficial layer of bubble-rich, very reflective ice is down to a couple inches thick, and it's a little bit hard to see on the screen here. It looks better on the computer, so those of you watching online actually have a better view here. But most of the image here, we have dark, clear ice down in most of the depth of the hole there. So we're getting a lot of melting from the top side. There's almost certainly some melting from the bottom side, but the heat is all coming from the top. So that limits the process there. As we get down closer to a foot, we've completely lost that surface reflective layer. So all that bubble-rich, basically snow and water that's flooded into the snowpack is gone, and we're left with this hard, clear ice, which is now at the surface. You can start to see a little bit of this candling phenomenon, where the ice is basically melting unevenly. You get little pinnacles that stand up, and then it's melting into the ice pack. So it gets a very rough, irregular surface. It can be from some of those dust particles absorbing more energy, and those, as they grab heat, they will sink into the ice further. And where there was cleaner ice, they tend to stand a little higher. So 1.2 feet. Get down towards a foot. The whole ice surface now, when you look out across the lake, is becoming much darker. And instead of being a big reflector, this thing now is a big light concentrator. We basically created a greenhouse. You have nice clear ice, and it's actually, the ice can be remarkably clear. As it freezes very slowly, any particulates in the water, any impurities, so things like the naturally occurring humic and fulvic acids that might add some color to the water, those are rejected from the ice, and so the ice is actually fairly pure water. Has very few dissolved solids, doesn't have a lot of the natural organic acids in it. So it's essentially a nice clear pane of glass, and all that sunshine is now going right through there and into the water column. And so we're basically trapping all that heat in the water column and keeping it separated from the surface atmosphere. So at night, it's like that greenhouse glass, keeping the heat in our greenhouse. And it also serves as a protective layer. It keeps any wind from moving the water column. So the water in the lake here is still dead calm. It's seeing very little effect of any wind at the surface at this point. And at this point, we're getting melting along the shore, and we're getting a few little patches opening up here and there. Get it down a little under a foot on this little cloudier day. But same thing, it's a nice dark surface. It's basically all that light that's hitting that ice is just going right on through into the lake. There's very little reflection off the surface. So even on a cloudy day, there's still a fair amount of heat energy in that sunlight. Our ice is thinning, and we're starting to form these candles, which are nice vertical crystals of ice. Basically run the thickness of the ice pack, maybe an inch or so in diameter. And as the ice breaks up, at some point you'll have a whole bunch of these floating at the surface for a short period of time before they go ahead and melt. And then we get down almost to a half foot. We're getting a lot of melting along the shoreline, and as we melt out along the shoreline, that gives some room for the ice pack to start shifting a little bit. And then as that ice pack can shift, that might be one mechanism that would disturb that water column. And then down in the corner here, you can see just the edge of my little kayak. When it gets down to a half foot thick, no way you're going to walk very far on this. And so the method seems to be you have one knee in your kayak and the other foot out, and you kind of scooter along the ice. All knowing that if you overdo one of your pushes and tip into the water, you're going to get very wet, but at least it's sunny, and air temperature is probably, in this photo here is probably up 60, 65, so sunny and fairly warm. You get cold, but as soon as you climb back in the kayak, you'd be warming up again. So not life-threatening. Yes. So the ice is getting quite thin here, and you can see our little tape here, which is a measuring tape with two conductors encased in the plastic. It's marked off in feet, tenths, and hundredths of a foot, and then has a temperature, conductivity, and there's temperature and conductivity on this particular probe. And then so this is April 21st, and then the 22nd, the ice is rapidly disappearing. Now we're paddling instead of scootering in the kayak. So one day, most of the ice goes, and with a little bit of fog in the picture, you get an idea of just the heat transfer that's occurring here. Very cold water evaporating into the air, condensing a little bit of water vapor there. So, in 2014, I went out a little more regularly. I tried to get out through the depth of winter about once a month. And then as we got a little bit warmer, we're approaching the spring, I was trying to get out once a week, and then picked up the pace a little more. But again, we see the same thing. In the dead of winter, we have quite cold water, and that cold water below, so the less than 4 degrees Celsius water, is extending down into the water column. Change scales here, it's now meters, but even 5 meters of depth, we've got water that's probably not quite, it's getting close to 3 degrees Celsius water there. So the depth of winter, that cold is slowly working its way into the water column. And so the first thing that seems to happen here is that that very cold water, less than 4 degrees C, slowly warms up. Within the ice pack, though, the water is near freezing or right close to zero, as we would expect in the ice pack itself. It's not always exactly zero, because the hole that you auger in allows some convection within that augered hole. So it's going to be a little bit of a mixture of some of the warmer 4 degrees C water coming up into your 0 degree hole. So that's the first part of the process. We warm the whole lake up something close to 4 degrees Celsius. And this fits very well with our expectations. Our maximum density of water here is right about 4 degrees Celsius. And as we go to colder water, it's a little less dense. And then as we go to warmer, it becomes much less dense. And this is actually one of those really important features of water. It's a little odd compared to most compounds in having its maximum density not immediately before it freezes. But what this means is that lakes freeze from the top down. If water had its maximum density at 0 just before it froze, it would actually freeze from the bottom up. And that would make life kind of tough for the fish and the other critters in the lake. If you turn the whole thing into a block of ice, not to mention it would take a very long time to melt in the spring. So this is a rather nifty feature of water in terms of having life on planet Earth. So maximum density here about 4 degrees C. And so then we got busy here. As the ice started getting thinner, we were out basically every other day or so. And very quickly, from April 11th, or maybe starting on somewhere in the 9th or 10th, and going out to the 21st, the water very quickly warms up underneath the ice. In this case, we got up over 7 degrees Celsius before it finally melted. And again, it's a fairly thick region that looks like it's about 2 meters at the warmest point. So that's about 6 feet. And then it extends down, that warming extends down close to 10 meters, which is 30 feet. So we're getting a lot of heat in the lake. And there's still almost a shadow of that, that ice water on top here. The thickness of that layer doesn't thin very fast. So even though the ice is melting, that water, that melted ice, is hanging out near the surface. In terms of the conductivity of the water, and this is just a measure of the dissolved ions in the water. If there are more dissolved ions in there, it conducts water better. And if it's very pure water, essentially distilled, or in this instance, it's freeze distilled, the ice, as it melts, has almost zero conductivity, and it produces a layer that stays in position almost to the end. And then throughout the rest of the water column, we have a fairly uniform conductivity with a very, we're starting to see some higher conductivity layers at the bottom few meters. And this may be some of our groundwater coming into the lake at a little higher dissolved solids. One of the other trends we'll notice is that we go from a little bit lower conductivities earlier in the process, and as we move closer to spring, this conductivity is just ever so slightly increasing. So we're interested in how groundwater fits in this process. We know that when we're growing the ice pack, we're rejecting ions from the ice as it freezes, and those get dumped into the water column. So there could be some concentration just by the freezing process, although by February here and going into March, we probably aren't adding much to the ice pack at this point. So it could just be a factor of groundwater flowing in and essentially no evaporation from the lake. Very little rainfall, further diluting the water. So we have some issues to address and figure out here. We're pretty sure it's not simply instrumental drift, because we do check our instruments against standards each trip out. So it seemed like they were calibrating nicely.
Groundwater temperature profile reflect that, because groundwater is 7 degrees or something.
Yeah, groundwater would probably be up maybe even 8 degrees Celsius. And I think that's part of, we see a little bit of, at the very bottom, we have this higher, very high conductivity. And we also see a little bit of a rise in temperature at the very bottom. So that could be some of that groundwater coming in at a much warmer temperature. And so when we zoom in here just to the top couple meters, we can start to see that shadow of the melted ice. Our ice pack here in the dead of winter probably got a little over 2 feet thick. And as it melted, we maintained a fairly low conductivity water to about that 2-foot depth, almost to the edge. We get a little bit of mixing in our augered hole, which seems to skew the results a little bit, but it's very interesting that that layer of water on the very top seems to stay in position. So you have some very cold water at about 0 degrees C. It's basically the melted ice that again was pure water, has very few dissolved solids, has very few organics in it. And it turns out that those natural humic and fulvic acids are very good at absorbing sunlight, particularly in the UV range. So if you have very optically clear water, that solar energy can go right on through and get deeper into the water column. And then below it here, we have fairly uniform conductivities. So we do seem to be getting some convection in the lower layer, but it's not penetrating up into that shadow of the melted ice layer. So there may be enough density contrast there. We're not sure. We have been playing around with some light sensors. This is one that we've got taped to the temperature and conductivity sensor, which is right here. And then we have a weight here. Just happen to have a convenient weight along. And then rigged up our light sensor with a couple loops here. And then the little sensors, the little silver piece just above the lip of the little ice skimmer for the ice auger hole. So we've got our little sensor pointing up, and then we can lower that down through the ice and try to measure where some of this light is being absorbed in the water column. In this case, the sensor can split out some of the parts of the spectrum. So you can see where some of the redder wavelengths are penetrating a little deeper, and blues and greens are getting pulled out a little bit earlier. And as we get down to about 10 meters depth, most of the sunlight has been absorbed at that point. So we're still playing around with these. This particular sensor, the biggest problem is at near the surface, we're basically overranging the sensor. It's too bright out. And then we're trying to figure out what you normalize that very bright overrange signal to. So we set up a little bit different lake. This is a lake up in Cass County in central Minnesota, Shingabee Lake. The nice feature here is the USGS maintains a research station here, and they have a permanent raft on the lake. So rather than trying to go out on the lake ice as it becomes increasingly thin, you just set up your data logger out on the raft and then wait for the ice to go out, and then you can paddle out in your rowboat or canoe and retrieve the data. So much simpler, and plus the data logger is there 24 hours a day. Like Shingabee, I don't know how many people have heard of it directly, but it's actually been in the paper just April 26th, Sunday. There was a large article about our good buddy Dallas Hudson here, who's doing some very interesting fish tagging work on Shingabee. So Shingabee has been in the news here as well. So we deployed a bunch of thermistors at a variety of depths, starting out at like quarter, half meter, 3/4, 1 meter, and then opened up the spacing to about a half meter a step, and then pushed it out as we got deeper. And then Shingabee Lake is about 8 meters deep. It's about 25, 26 feet deep at its maximum point. So we deployed this, discovered fairly quickly that some of our deeper sensors fairly quickly, the waterproofing on the thermistor wasn't quite good. And so some of them, like the light green line, are chugging along up around temperatures of 5 degrees Celsius for a while, then they plummet down to 0. So when you first set up an array of sensors and deploy it, you figure out how good they are. And it looks like we were good to about 3 meters of water depth. When we got below that, it got a little dicey, although interestingly, our deepest thermistor at 8 meters survived throughout. So go figure. But we're working on building some better sensors. So this is just the temperature record at various depths as we go through the melt-out cycle here. And this is kind of ugly. Very deepest sensor at 8 meters in the light purple stayed fairly constant. And then a lot of the ones near the surface show a nice daily signal. So as the sun comes out, heats up the water column. At some point, it'll actually start convection in the water column, and then overnight, it'll kind of be cold break. So we can pull out all that data into something that looks more like the profiles from Square Lake, normalized here to 1 o'clock in the afternoon. And we see a very similar thing. Initially, temperatures are near 4 degrees Celsius. And then as we come up near the surface, we get a layer that, in this case, is at least 3 meters depth. You'll notice our sensors kind of peter out there once we get deeper. And just like on Square Lake, there's a nice shadow of the ice pack that's retained quite late in the process here. One of the interesting things with this particular ice out is normally, and almost always, if you talk to people that have hung out around lakes and watched them for a long time, ice never goes out at night. It goes out during the day. And so it's at some point you get some tipping point, and it's usually a nice sunny day where there's extra heat going into the water column, and maybe there's some wind to start jostling the ice a little bit. In this case, we got a terrible windstorm on the night of April 26th that took the ice out in the middle of the night. So Dallas woke up one morning and it was all. If we look at the cycle through a day, so this is just April 22nd to 23rd. We get some warming through the day, and initially the warming seems to come in here at a depth probably peaking around 2 meters. So that seems to be where we're absorbing most of the solar energy. And then once the sun sets, And as that water column is convecting, we're redistributing that heat closer up to the base of the ice. So we're seeing some convection here, but it's not penetrating that surface layer yet. So it's not, that warm water isn't hitting the base of the ice quite yet. So what are the factors that are going on here? We've got this density effect, which for most people's experience, it's the one we know about and see firsthand. That's why the ice floats on the lake rather than sinking. But in terms of mixing, getting that layer of melted ice water from the ice pack and mixing that with the warmer lake water underneath. Basically, you have to get convection through that layer of water. And it turns out that viscosity may actually be a bigger effect here. To get convection, we need to have these inertial forces overtake the viscous forces, which is this Reynolds number, and it's basically defining whether or not we maintain a more laminar type flow or if we get into convective flow. So viscosity here figures quite prominently. It's in the denominator here, the viscosity effects. And here we've added to the plot. This is our density curve, and the scale for density is on the left side of the graph. And the interesting thing about the density, this whole game with density is played at the part per thousand level. We have talked about changes in density of 1 or 2 parts per thousand. So relatively small changes in density. They're important changes, but in terms of this convective mixing, that's not a very big gradient to overcome. On the viscosity side, though, which is on the right-hand scale, we're going from at 0 Celsius, the viscosity here to about 1800, and even by the time we get to 4 degrees C, we're approaching something between 1500 and 1600. So we've got 200 parts out of 1600, or about 1 part in 8. So this is something, the density effect here, something larger than 10%. So a pretty big change in viscosity. And so that is one thing that can help limit that mixing of those layers. And then we didn't do as much measurement this year. We got out this year on April 1st on Square Lake. And water being April, I don't know that we got to quite as warm a water, but around noon on April 1st, we had a layer that was about 6 degrees Celsius. There was a little peak down just a little more than 10 feet down. And so we probably had some convection going on at this point already, and didn't seem to quite reach the same types of peaks. But a very different year. We're basically 3 to 4 weeks ahead of where we've been the last 2 years. So the sun isn't near as high in the sky. Days aren't quite as long. So not getting the same solar energy into the water column. Yeah, we didn't have to melt off that surface layer. That was gone very quickly this year. So we've got some plans here. To start out is just test driving some of the sensors, see how well they work in cold environments, and make sure things didn't freeze up on me. But we found something interesting. I never ever expected that there would be water that warm immediately under the ice. And there's some very large implications there. The lake is already stratified before the ice is off. So in terms of your oxygen budget for the lake, If the lake is, if it can remain stratified through the ice off, you're never going to mix much oxygen down into those deeper layers. So in the spring, you might skip that oxygen mixing altogether, and that could have large implications for the biology that's living in the deeper parts of the lake. You might still have the good fall mixing, or you have to essentially cool the whole water column down to 4 degrees Celsius before you can start forming the colder water on the top. But a lake that mixes twice a year is going to have a whole lot more oxygen through the summer in the deep water than one that mixes once a year. Or if you take the next step, you can go to a lake that is just permanently stratified. So we have some work here. I think there's a lot of interesting research here that has some large implications on not just the water column, but the biology in the lake as well. What kinds of fish you can support, what kinds of invertebrates, and so on. One of the tools we'd like to get out here are some of these little Arduino loggers, which I don't know if any of you guys have played with them. They're basically a full-on PC computer on a chip. They don't have a monitor, they don't have a keypad, they don't have a disk drive, but they're a full-on computer, and you can buy them for about $40 a piece. So you can hook up all kinds of sensors, all kinds of measurement devices, hook up some kind of little USB memory chip on there. You can store unlimited amounts of data and do it very cheaply. So in an environment like a lake ice, as it's melting and then as it goes off, that can be a little rugged. We had our raft on Shingabee with a very strong wind. It turned out that our raft basically went almost all the way across the lake in the wind. But we did have a nice big raft, and it was big enough. It kept our data logger dry and out of the water. But that's a pretty large construct. With these Arduinos, we could basically develop something that would fit maybe in a small buoy that would maybe be a foot tall and 6 inches in diameter that we could put out on the ice. And it's fairly cheap, so if we got this crushed by the ice, we wouldn't be heartbroken. But if we had several of these out there, hopefully a few would survive, and we could get some good usable data through this ice-off process without the effort of trying to go out on thin ice. And particularly being able to do it around the clock would be nice. So I think there's some real science that can come out of this. We just got to develop the tools to get out there and play with it. So here's one of those little Arduino boards. This guy's like 3 inches by 4 inches. They're just amazing little toys. They're one of these things that they use at the elementary schools now in the little maker classes. They build, hook up little motors and actuators of all kinds and build little robots and little carts that run around and do all kinds of things.
So that would float in the buoy, and then the sensors
would be hanging down on a cable below. And then with some of these, you can also set up either a radio frequency or a Wi-Fi network. So you could actually be collecting data in real time from the middle of the lake.
If they got crushed,
You'd still have the data up to the point they got crushed. It could be kind of fun. You could have your annual contest, your annual lottery to see who can guess the ice out date.
Without having to put a car on it.
Without having to put a car out there. And then you could actually sell more unique times instead of a day. You could put it down to the hour or minute if you got serious about this.
So do you see these replacing the Campbell data loggers? Or just
They're a whole different aspect. One of the issues is being very inexpensive. One of the ways to make them cheap is they do not have a very good clock on them. So for long-term measurements, you can get some significant drift. Which if you have some kind of communication with it, you can reset the clock time periodically. But I think there's still a place for the Campbells for more permanent, like the meteorology stations. Campbells are probably going to remain for quite a while. But these guys, you could basically deploy 100 of these for every Campbell you had out there. So
what is the cost?
by the time you get sensors and all, you're probably talking a little less than $100.
Including sensors?
Yeah.
Wow.
So, I mean, it changes the game.
Be great recap.
Yeah.
I want one for my lake.
Safety in numbers, yeah. So, you know, if your Camel gets destroyed, you're a little sad.
You're a lot.
Very sad. Yeah.
Yeah, it hurts. And these guys, yeah, you'd be sad to lose one of these, but not too bad. So anyway, these are great fun. We're one of our new hires at the University of Minnesota is actually one of his hobbies beyond geology